Hello everyone, I'm Manish Chiti and I'm here to talk about my project called MNIST Classification and Clustering. In this project, I explored how different machine learning techniques perform when applied to a subset of MNIST, specifically the digit handwritten dataset. Specifically, I worked with 6 digits 2, 6, 4, 3, 10, and 5 and used both supervised and unsupervised methods to analyze and classify the data. My goal wasn't just to build an accurate classifier, but also to understand how dimensionality detection and clustering reveal structure in data and how the algorithm choices can significantly affect the results. One of the most surprising results came from the binary classification task. Distinguishing between 2 and 6 digits, I started with a linear support vector machine and reached the highest accuracy of 98.04. That already seems strong. But when I switched to a Gaussian RBF kernel, the accuracy jumped to 99.70. That result stood up to me because it showed how nonlinear kernels can capture hidden complexity that a linear model simply misses, especially in something such as varied as handwritten digits. I also wanted to see how well multi-class classification works. So I implemented both one versus all and one versus one strategies using support vector machines across all the 6 digits. Here again, the one versus one approach clearly performed better. It achieved 92.66% precision and sensitivity compared to the 1V all where it had about 88%. What I found interesting is that a 1v1 handled the fine-grained differences between the digits much better, which made me realize how even small decisions can lead to a better real-world performance. Next, I turned to clustering, applying k-means without using any labels. I experimented with different values of k and found out that k equal to 6, which matches the number of digits, gave the most meaningful and interpretable clusters. It was fascinating to see, even without labels, the algorithm could uncover structure in the data. Some cluster centers even looked like clear digit prototypes when visualized. To push it further, I applied two-dimensionality detection methods, kernel PCA and Laplacian eigenmaps. With kernel PCA, I saw that while it reduced the dimensions, it hurt the classification performance, likely because it captured global variance but lost class separating detail. On the other hand, Laplacian eigenmaps perform impressively well, especially in multi-class classification, where 1v1 support vector machine on the Laplacian reduced the data, which achieved over 93% precision. This taught me that preserving local structure in the data can be more important than simply reducing the dimension. Overall, this project helped me connect theory with my practice. I not only learned how support vector machine and clustering work, but I also understand how preprocessing, feature scaling, and kernel choices directly impact the results. More importantly, I learned that the interpretability of the results, specifically in unsupervised learning, is important such as the raw accuracy. Thank you so much.